and then everybody can. So in this small session, before we dive into the solution of the exercises, I wanted to say something which is relevant for homework number 2 and also homework number 3, in particular when it comes to the numerical exercise. So let's now look at the homework 2 and also partly homework 3. And this deals with exercise number 6, which is the numerical part. Now, what you have in exercise 6 for homework number 2 here is a solution for the motion of an object. This is actually a golf ball. And what you have is a solution for x, which depends on time in some specific way. So there is a specific time dependence. And in this exercise, the time dependence is now related to some cosine of time plus something. So now we're just going to be very generic here. And then we have a time dependence for the y direction, and that could be some sine of time plus something. And we have a similar one for the z direction. And where we could have another type of function, we could have something like gt squared plus something. Now, what we have in this case is a solution which depends on time, and we have 3 spatial dimensions. So in Python, what you could do now is to define, Python, we could define an array which contains the time variable. Define an array which depends on time. And the way we would do that could typically be something like us defining a time step, delta t. Suppose we just define that to be 0.1. Then we could define another variable, which would be the final time, t final, which could be something like 10 seconds, just to give you an example. Delta t could be just 0.1 seconds. And if we do this, what we could do then, what we have is then a array which we could define as t equal to something like np range, and we would define an initial time 0, and then we have the t final, and then we would have a delta t here which specifies how many time steps we're actually going to have here. Now, with that, we have defined a time step, and this means that x, y, and z, they are defined as functions of t. And then, when we have these as functions of t, what could be done is that we could define a vector r, which depends on t, which is now simply given by x of t, y of t, and z of t. Now, Python has a very compact way by which we can define these quantities. So the basic message which I want to convey to you is that, one, what we could do is that we could define an array for time. We need to do that. And then we could define specific arrays for x, y, and z. But we could also define an array for just r, which then would be the vector which points to the specific point as a function of time. And in that way, in Python, we could compactify this in the following way. So let's just jump over to the way we can do this in Python. So let's just go to the specific Python code here. And I hope everybody sees now. So the whole message is that we have compact ways by which we can set up an array in Python. So if you look at this specific homework, one of the things we could do now, we could define the final time. Then we could define a time step, delta t. And with that, we can now define an array like this one, which now contains the specific discretized values of t, which are defined by 2.4 minus 0, which is initial time, which you can see here. And then we have a tf here, which is the final time. And this would then set up a given number of discretized points according to this delta t. On the other hand, what we could have done here, and I just wanted to show you that, we could have done t initial like this, just to give another example. T initial equal to 0. And then we could have defined the number of integration points or the number of time steps of time values. And we could call this n, and we could say that is equal to 100. Then our delta t would be equal to tf, the final time, minus t initial, and then divided by n. Then we would simply define a time step which now is given by the final time minus initial time divided by n. Based on that one, with this value n, we could then initialize an array, which we could say t is np, we put all the values to zeros, and then we would simply write n here. And then we have defined an array which contains 100 values, and then we can set up these 100 values here. So then we would typically say for I equal to length of t, like this. And then we would simply say that the t of I, so this is one way of setting it up, t of I is equal to t0, t initial, which in our case is 0, plus I multiplied with delta t. And then we would have a variable t, which now contains all the time steps. This is an alternative way of setting up the time domain. So in this case, we're not going to use that. So let me just comment them out again. But this is just an alternative to what we could do. And then in the case which we have chosen here, what we've done is simply to take the arange function in Python, which you see here. And with the arange function in Python, we can then define the different t values automatically by having predefined a step size, the initial time, and the final time. This is often very, very useful. Now, so there are two main ways by which we can initialize and set up an array of discretized time. Then clearly, if you look at x here, this variable here, you see now that there is a t dependence here. That means that we don't need to define x, y, and z as arrays because they will be automatically defined by the size of t. So we will allocate x of 0, x of 1, x of 3, etc., as a function of time. And this is something which is extremely handy because then instead of us having a loop and setting up the values, we are using this vectorized form, which Python offers us, and we get an equation for x, which is almost identical to the mathematical expression which we get when we solve the exercise by pen and paper. So these are just ways by which we can now set up the arrays. And what you would get then is typically something like this when you plot it. So I use the scatter function when I'm plotting. So I plot x, y, and z here. Alternatively, if you now look at this definition here, what I could do, I could take an alternative way and I could define now an array R, which now contains x, which you see here as a function of t, y as a function of t, and z as a function of t here. This is just an alternative way, and you see now that I have defined the first element of this array to be the X value, the second to be the Y value, and the third one to be the Z value. Now, this is something which is very compact and which can confuse us in the beginning, because this includes also time. So in principle, what this is, it is actually a matrix which contains the number of time steps, the X, Y, and Z value. Now, I wanted to show you another example, but please feel free to ask questions about this kind of Python technicality. So if you have any questions, I mean, please let me know, or let Shu Yu know. She's in the STEM building, or you can just put it in the chat. And in case this is something you're not too familiar with. The other thing I wanted to show you is something which is more relevant for the next homework. And I know that some of you have already asked me about the next homework, and if there are compact ways by which we can encode the solution of the differential equation, where we integrate up till the final position of a falling object. So let me just show you a little bit about the parts of that specific homework. And I'm going to direct you to the, unless you have any questions about homework number 2 here and the numerical part. This is in the lecture slides for this week, and it deals actually with the integration of these equations. So what we're having, we have the integration for the falling object, and we can solve the differential equations analytically, as we discussed last time. And when we do that, we're actually solving an equation for v of x. There's an equation for v of y. And similarly, there's also an equation for x and y here. Now, when you're coding this in homework number 3, what you could do now is to write separate lines of code for the x, y, and z direction. In this case, it's only x, y. And in this case, we have time here, which we would set up like this. We have defined a final time. We have this delta t, the time step. And then we are setting up an array for the velocity in the y direction, the position in the y direction, the velocity in the x direction, and the position in the x direction. Then we define the initial conditions. So when you're solving homework number 3, take a look at the examples which you find in the lecture notes for this specific week, because that shows also another way by which you can now, write the solutions in a more compact way in terms of an array which is 2-dimensional, and I will show you how. So what you see here is more the kind of brute force solution. You need to find the acceleration. This is a task in the exercise next week. And then with the acceleration, you update the velocities, you update the positions, you update the same thing in the y direction, and finally you have the final velocities and final positions. So in this case, we have an array of length, time. So, and for each direction, x and y, we specify a given variable, which is vx, x, vy, and y. This is not the most elegant and compact way you can do it. And you will find if you scroll down in the lecture notes, so actually here we haven't defined a of x. So if you scroll down a little bit in these lecture notes, you will find a smarter way by which you can do that. So let me show you that one. And I'm going back here. Not that one. That was that one. Let me just bring. So if we scroll down and look at the solution for the exercise next week, I just wanted to show you this more compact way by which you can define the x and the y directions. So in here, in the first example here, you see the same thing which I showed you in the other slides. So we just have simply defined an array which depends on time for the y directions, velocities, and positions, and the same for the x directions, as you can see here. Now you can rewrite this in a more compact way by defining a 2-dimensional array. So what you would do now is you would define a velocity, and you don't need to make a known variable for X and Y, but you could define an array, which is actually a matrix, which contains a number of time steps. The first element here is X, and the second is Y. Then you can define something like this array here, which is the initial condition, R0, which now has the initial X value and the initial Y value. And here's the initial velocity in the X direction and the initial velocity in the Y direction. This means that now you put that time t equals 0. So it's a kind of notation which is a little bit confusing, because you would think that this is a variable which has only one dimension, but actually this has a dimension time times the spatial dimension. So it's actually a matrix. So the way you see this here is a much more compact notation. And here I'm looping over time, and then I'm updating for each time step. And this makes an update of both the X and the Y direction. So this is a much more compact way by which we can define arrays when we move from one dimension to two dimensions. So this is basically what I wanted to give as a kind of hint for the homework today and also the homework next week. And we're sorry for the delay which we had, but I hope this can be of some help when you're looking at the homeworks for this week and next week. And we are going to repeat this in the beginning of next week as well. So I'm going to stop the recording. I'm going to place this kind of small hint for the first exercise online, and then we are going to use the rest of the time